this. Hey everybody, good afternoon. Thank you for joining Jenna and I today. We're very excited to present to you today. We're going to be presenting on improving patient care with large-scale data engineering and machine learning. My name is Joe Langreo, and I'm part of our AWS professional services team. Jenna?
Hi everyone, I'm Jenna N. I am also part of the AWS professional services. I lead a team of specialists focusing on healthcare data and machine learning, and also high-performance computing. I'm really glad to be here. Thanks for coming.
Thanks, and one more thing before we start this off. This is actually based on a project that Jen and I worked on together, and so we're very excited to share some of our learnings from that. All right, so there's 4 main topics that we'll be highlighting in our presentation today. First is, why is AI challenging in healthcare today? Second, using traditional methods and including traditional AI methods. What are some of the common use cases and challenges that are faced today with our customers? Third is, where does Gen AI and transformer models fit into this? And how does it help address those common use cases? And fourth, like we said, this was something that we did on a project. What would we improve upon? So first off, what is AI ML and why is it challenging in healthcare today? Simply put, it's a data problem. Over 80% of data is trapped in free-form medical text. As you can see here, some of that could include progress notes, medical notes, visit summaries, and if you think about it, a lot of that patient-rich information is trapped in that free-form medical text. And this is petabytes of scale. It's growing, and if you work in this field, you know it's growing daily. So that information is trapped in unstructured data. It could be multimodal, contextual, but since that information is trapped in that unstructured data, in order to be used by EHR system, it has to be transformed and extracted into structured type data. And the process to extract this data is time consuming and labor intensive. And if you think maybe a smaller medical facility or hospital may not have the staff or skill expertise in order to spend to get that key extracted data, and that is why it's so important to be able to solve this problem for different medical centers. So there's 3 common healthcare use cases that we'll be highlighting today. Again, this is a lightning talk. We only have 20 minutes. There's so many use cases, but these are the 3 we'll be focusing on in our presentation. First off, patient care coordination. This, for example, an organ transplant and cancer treatment planning. If you think about a situation where you need a plan for a patient for their organ transplant or their cancer treatment, and you have to be able to extract that information in that is in that multimodal contextual data. Second, patient transfer between healthcare organizations. Many of you probably work in the medical field, and if you think about you have to transfer a patient from one facility to another, that data is trapped, and it's going to take some time to extract that data, especially with different places using different EHR systems. Lastly, and this is the largest scale definitely of the 3 healthcare use cases that we're highlighting, is population healthcare analysis with government departments. This, if you think, it's not just one patient, not just 10 or 100 patients, tens of thousands, hundreds of thousands of patients, and it's really important to be able to solve this problem of getting that unstructured data. So what is the typical process of getting that key insights? So first we're going to highlight manual method, then we'll get into traditional AI ML method, and then we'll get into Gen AI. So typical process for analyzing healthcare data is 3 main steps. So the first step is collecting the document images, usually using an EHR system to collect the document images. Oftentimes this is faxed, emailed, and this is in many forms that is in that document images. Second main step is curating that data manually. So now that you have that data in your system, you have to have the medical expertise in order to extract that key information. And third is asking a human expert next steps. Are you going to accept the patient? Are you going to transfer that patient? Maybe you have to deny that patient, you don't have space. So you have to have the medical expertise, and it starts from being able to extract that key information. So traditional AI ML, so we're going through the steps. So we started off with a typical manual process. Now we're going to talk about traditional AI ML and where it falls short. And then we're going to introduce Gen AI. So with traditional AI ML, there's 3 main problems that we'll be highlighting today. First is incomplete extraction of document images. So usually in traditional AI ML, it uses OCR, or optical character recognition, to extract text from documents. However, if you've used this before, it's not complete. Meaning it doesn't get the complex data complex type of data information that you need. So tables, forms, images. So if you think about it, a lot of that rich information is in that complex data, and OCR just doesn't cut it. So oftentimes medical experts will just go back to doing it manually. Second step, bag of words technique. So let's say you have the data extracted with both OCR plus manual extraction. Now you want to get some insights from that. The typical traditional AI/ML method is using bag of words, or better known as keyword plus count search. So this is, does it exist? Does it not exist? And if you just think about the simple issue with that is it doesn't have any contextual information. It doesn't have any relationships. And you're going to want to understand the relationships in order to be able to figure out what to do for that patient. So let's take a simple example of a headache. So let's say there's a person that has a history of concussions. Using this bag of word techniques, maybe on this current medical report, it only has the word headache once or twice. As a medical expert, you would know, hey, they have a history of concussions. It's a more serious issue than just a 1 or 2 time headache. But bag of words, traditional AML, wouldn't be able to find that out. And third, we introduced a little bit, but using simpler ML algorithms that are not contextually aware won't be able to get that contextual information across that a medical expert would be able to, given the time needed to be able to extract that. And that's where Gen AI and LLM comes in, to be able to process this data at scale, but also get that contextual information. And with that, I'm going to be turning over to my colleague, Jenna.
Yeah, thanks, Joe. Yeah, so as Joe highlighted earlier, using traditional AI/ML methods can have a number of different problems. So in order to address that, we created a solution pattern that can be fit for a number of different use cases that uses Gen AI and transformer models. And I'll talk about exactly how that works in 3 steps. So the first thing, as Joe pointed out earlier, using the regular OCR, optical character recognition method, is not very good at picking up all of the details when you're extracting text out of document images. So what we focused on was by using Amazon Textract to improve that process. And how does it improve it? Because it goes beyond a simple text extraction. So first of all, it's able to work with handwritings as well as distorted text and document images that have very low image quality. And we found that even documents that were made back in the 1700s that has completely 100% handwritten EHR records from back in those days, Textract is able to successfully extract those text out of those images. And also Textract can recognize the layout of the document. So understanding what is the header, what is the footer, where is the overall text box, where's the list, Textract is able to automatically understand the layout of the document. It can also recognize the structure of tables, so the rows and columns, what those are. And then separately, the forms. The different forms have key value pairs, and that's a very important information, and traditional OCR technology would not be able to handle forms unless you are manually configuring that for every single specific form format. So Textract is one of the things that we implemented. And then another thing that we wanted to do was we wanted to mimic how humans read documents. Because if you think about it, if you give a patient chart to a medical expert, that medical expert is not reading a novel. They're not just reading every line and thinking about, what's going to happen next. What they do is, in fact, they're actually constantly asking questions as they're reading the documents. They're not just, willy-nilly reading the document. So what we wanted to do is actually mimic that process by using Gen AI. So if you think about what experts do, for example, when they're thinking about patient transfer, they will be thinking about, how many times was this patient hospitalized in the last 6 months? If they're thinking about liver transplant patient, they will be thinking about, what is the MELD score for that patient? So what we wanted to do is take those questions that a human expert would think about, and then essentially convert that into prompts, so use prompt engineering in this process. So what we did is we would ask a clinical expert and ask them, okay, when you read this document for this purpose, what are the questions that you would ask? So collect those questions, and then once we have curated those questions, then we would convert that into prompts using prompt engineering and have the Gen AI agent to ask and answer those questions on the documents. And then we would compile the answers from the LLMs, the Gen AI agents, and then that would become the summary of the information of the text. And this works really well because many times a lot of the documents that we find in healthcare, there can be many documents per patient, per case, as well as each document can have hundreds of pages of notes. But not all of that information is relevant for a particular business use case. So when you do this process, you are essentially extracting the most important information from that whole document into a very small amount, essentially increasing the signal to noise ratio before you do the next process in your step. So the third thing that we wanted to highlight is that we then wanted to take that summary information and then directly feed it to a transformer model for the next predictive modeling task. And this works really well because transformer models have the underlying architecture that's very similar to LLMs. So what that means is that instead of creating your text data, taking your text data and then making it into a specific features, like discrete features, whether it's continuous variable or categorical variable, you actually take that input paragraph as is and then conserving that context as is and directly feeding in. So you skip the whole feature engineering part, which makes this approach very, very scalable, regardless of which business use case that you're trying to tackle. And so taking that input text, it'll convert into mathematical representations of that text, and then you can configure the last layer of your neural network to whichever business use case that you want to look at. So in this particular case, it could be whether you want to transfer this patient, yes or no. And then we also found that using SageMaker is a great way to apply transfer learning, because a lot of these transformer models are available with pre-trained with clinical data. So you don't have to start from zero, but you're actually taking something that was already trained and then modifying it further for your own use case. So as I said, our approach overall has 3 steps: data extraction with TextRact, creating a summary using GenAI using Bedrock, and then lastly, transformer-based predictive modeling using SageMaker. So now going into each of these steps in a little bit more detail using architecture diagrams. So I mentioned to you already that we're taking PDFs of documents, and then we initiate the TextRact job using a Lambda function, and then the output of that TextRact job will go to an S3 bucket. What we can do is that because this particular step is something that you would do over and over and over again for many different patients, what you can do is you can coordinate that entire process using step functions. And in particular, in step functions, there's something called map state. And that process will allow you to do these repetitive tasks concurrently at hundreds of thousands of tasks in one go. So you can really utilize a part of AWS Cloud to parallelize your processing, so you're not waiting forever. And then once you have that text extracted, then you would feed that into your foundation model using Bedrock to do that automated Q&A to ask questions, specific questions, and then get the answers. And then once you have that answers as summary text in another S3 bucket, then you can initiate a transformer model to predict what is patient transfer yes or no, as for example. And then in here again using SageMaker. So there are still a number of different things that we can do to further improve this pattern. So the first thing is by using vision language models. So vision language models are these multimodal LLMs that are trained on both images and text data. So it's able to process document images, wholly, and there's a lot of active research going on right now to compare this technology to traditional OCR methods. So this could be something interesting to experiment, how this would compare to textract. Another thing is to implementing guardrails, because as you know, LLMs can have problems like hallucinations. And in our case, we made sure that we would compare our LLM outputs and then validate that by using human subject matter expert evaluation of those outputs. But there is also an automated guardrail features available using Bedrock, where it would do a contextual ground checking to see if there is any hallucination in the response of the LLM. And then lastly, we think that we could also further optimize the cost of running these processes by using AWS Trainium, which has shown that you can save up to 50% in the cost to train. So I really hope that you took away something useful from our talk. As I said, the main takeaway points here is that one, really automating that data engineering and then mimicking the human process by using GenAI. So that's number one, GenAI-driven data engineering. And then secondly, massive parallelization by using AWS cloud technology such as Lambda, step function, and so on. So thank you so much for your attention, and we'll be right over there to take any questions that you may have. Thank you so much.